So in previous lecture, we discussed the compact linear operator. So in the definition of operator, it is a linear transformation, and compact linear operator means for every bounded set in left hand side, then the image of that bounded set is relatively compact. So that is a definition of compact linear operators. Now next theorem is, let n and n dash be a normed space and T is from n to n dash is a linear operator. If T is bounded and dimension of its image of n is finite or less than infinity, then it means a T is a compact linear operators. So these are two condition is given. One is T is a bounded operator, and second dimension of T of n is less than infinity. Now first I take dimension of n is n dash is less than infinity, right? And T is from n to n dash is a bounded linear operator. So this is a bounded linear operator. If T is bounded linear operator, then by definition, if it is bounded set, then its image is relatively compact. That we want to prove. This is bounded operator. Our purpose is to prove T is compact linear operator. So we will take some bounded set in N and prove that its image is relatively compact. So in order to prove that, suppose M is bounded subset of N. Then by definition, there exists a positive constant C such that norm of x less than equal to C for every x belongs to M. Since T is from n to n dash is bounded, suppose this is from n to n dash is bounded, then by definition of bounded operator, norm of Tx less than equal to norm of T into norm of x. Now by equation number 1, this is less than 1, this is C into norm of T, and this entire term is less than infinity. So norm of Tx less than infinity. So this is a bounded. Less than infinity means T of x for every x belongs to M is a bounded set. Then it implies T of M is a bounded set. Now its closure is again bounded. No, its closure is closed as well as bounded. We know that in finite dimensional norm space, a subset M dash is compact if and only if it is closed and bounded. So this result is possible only in case of finite dimensional space. So here we take this is by given part. If this is less than infinity, it means this is dimension of n dash. So correct this, not n. It is a dimension of n dash, which is less than infinity. So it means this is a finite dimensional space, either D of n or n dash. If it is a finite dimensional space, then by that definition, this is a compact. If this is a compact, then T of M is relatively compact for every bounded set M in norm space N. It means T is a compact linear operator. Next result is, it is very important result, let Tn be a sequence of compact linear operator from norm space N into Banach space N dash. So in this case, it is a norm space, it is a Banach space. And Tn be a sequence of compact linear operator. If if this sequence uniformly convergent operator, then its limit is compact. It means if sequence of compact linear operator is convergent, then its limit is again a compact linear compact operator. Or we can say that the limit of sequence of compact linear operator is again compact. Clear? So that is our result. Now, this Tn is a sequence of compact linear operator. Now, this sequence converge to T. Our purpose is this T is compact linear operator. In order to prove this, first we take T1. Clear? So this is T1, which is a from n to n dash compact linear operator. Right? Then T1xk has convergent subsequence for every bounded sequence xa in n by definition of compact linear operator. And we know that if it has convergent subsequence, then convergent sequence are Cauchy, then it means it has Cauchy subsequence. We can say that. We can say that it has Cauchy subsequence. Clear? Because every convergent sequence is Cauchy. Then what we get? We get T1 x1k is a Cauchy sequence because it is a subsequence of that. It is a Cauchy subsequence for bounded sequence xk. Clear? Similarly, for T2, T2 x2k is a Cauchy sequence where x2k is the subsequence of bounded sequence xk, as in previous result. Continue the process. So it is if T1 x1k, then T2 x2k, similarly Tn xnk is a Cauchy sequence, where xnk is a subsequence of bounded sequence xk. Now, this, it is a first subsequence of xk, it is a second subsequence of xk, it is a kth subsequence of xk. And all under these operator, first sequence, under operator T1 is Cauchy, second sequence under operator T2 is Cauchy, and this operator, this sequence under Tk is a Cauchy sequence that we already proved with the help of compact linear operator. Right? Now, these diagonal entries, these are x11, x22, xkk. We represented these entry in the form of yk. So what is yk? Which is xkk. So what is this? This is again subsequence of xk, right? So because all these sequences are Cauchys, so it is again Cauchy sequence. This is again Cauchy sequence under this. Now, if we take these diagonal entries and these diagonal entries represented as yk, and this is a subsequence of xk, such that for every fixed n, this is a Cauchy sequence. That is Cauchy sequence with the T1, T2, and so on up to Tn. So we take only diagonal entries. So this yk is subsequence of xk, and this xk is bounded. If xk is bounded, then every subsequence is also bounded. So it means this yk is also bounded. If yk is bounded, the norm of yk less than equal to c for every n that is written in equation number 1. Clear? As we know that Tn approaches to T, then it means norm of Tn minus T approaches to 0 as n approaches to infinity. So this can be also written in the definition form. For epsilon greater than 0, there exists positive integer p such that norm of Tn minus T less than. This is this number is as per our requirement. So because at this place we know our requirement, so here we write epsilon by 3c because our need is this. Otherwise, we can also write it at the end. So just uh, it this space should be vacant, and you may be right at the end for every n greater than equal to p. Now, in particular, if we take this n, because this condition is true for n greater than equal to p, right? So in particular, we take n equal to p. So this condition is satisfied, and this is in equation number 2. Again, T and Yk is Cauchy sequence. Then again use the definition of Cauchy sequence. By Cauchy sequence, T and Yi minus T and Yj less than epsilon by 3. That is again depending upon our requirement for every ij greater than equal to m. M is positive integer. Again, we take in particular n equal to p. So this condition is again satisfied for p. This. Let ti and j approaches to m. That is here we used it. These are integer greater than equal to m. Now ty minus tyj. Ty minus tyj can be written in the form of first subtract tpye I plus this and minus this. Clear? Similarly, in this case, so in the first part, add, subtract tpyi and add tpyi. Again, in the end, subtract tpyj and add tpyj. So we get these three bracket, first, second, and third. Here subtract tpyij, yi, then add. So that is in this bracket. Here we add this yj, that is subtract in this case. So we get 1, 2, and 3. By using triangle inequality, this less than equal to first part, second part, third part. First and second part is same because here common is this yi, here common is yj. So by NOR, this can be written as, by definition of bounded operator, this can be written as this into this plus this into this. Here it is different yi and yj. So here tpyi minus tpyj. Clear? Now in this case, this norm is less than equal to epsilon by 3c. Again, this is less than equal to epsilon by 3c. And norm of yi and yj is less than equal to c. So that is in equation number this. This is less than epsilon by 3c. And norm of yk is less than equal to c. If this is less than equal to c, and this by Cauchy sequence, by using this, that is only applicable under this condition. That condition we choose already. So it means this is less than epsilon by 3. The total sum is epsilon. Then it means this norm, again it is norm less than epsilon for every ij greater than equal to n. This values. Now it means this tyk Cauchy sequence in n dash. Now, what is n dash? N dash is Banach space. What is Banach space? Banach space is complete. If it is complete, then every Cauchy sequence is convergent. And what we get? We get this is a subsequence of xn. Xn is bounded secant. Then its image has convergent subsequence, which is a definition of compact linear operator. So it implies T is a compact linear operator because xn sequence has subsequence which is yk, and under this its image. So Txn has convergent subsequence Tyk. So it means T is a compact linear operator. Now, from this definition, the above theorem is applicable only for uniform convergence. This is applicable. This theorem is only for uniform convergence. This is not applicable for strong operator, strongly convergent operator. So this theorem, which is applicable only for uniform convergent operator, and this theorem is applicable only for uniformly convergent operator, but not for strongly convergent operator, that we will discuss in the next lecture.